And in this talk, Kevin will drive the last nail in the coffin and will cover GLC5, which will be the end of the argument. So far, we know the dexterity, we know conservativity, but we still need this polyphasicness, and Kevin is going to prove it. And after Kevin's talk, we'll have a short break, and then we'll have a discussion session. Well, not exactly Q&A. I mean, you can also ask questions, but the idea is it will be discussion sessions about further directions. Right.
All right, so let me begin by kind of summarizing where we are. So the very beginning of the week, we constructed the Langlands functor. We noted LG. And this functor is linear over quasi colimits feature. And it had the key property of certain compatibility with Whittaker coefficients by its design. And then after a lot of work, we showed this functor had left the joint. And well, necessarily the left the joint makes the diagram of left the joint smooth. Well, you check. This is the functor classifying just the structure of heat. This is functor heat. Thank you. Okay, then we want to show LG is an equivalence. And let me first just informally summarize kind of what we said so far about LG, but not necessarily in order in which it was said. So, okay, we need to somehow understand this DF1G, and the theory of Eisenstein series allows you to understand the part that has to do with reducible local systems. And we basically explain that, okay, we know everything on that locus. So if you over the locus of reducible local systems, LG is an equivalence. Then there's irreducible local systems. How do we deal with that? Well, we need to somehow, at the very least, produce many things on the left-hand side that witness these. And here we use something really, really particular to the de Rham setting, which is Kac-Moody localization. And so this has to do with Opers, and there are these like irreducible local systems, and they have some generic Oper structures, and this FLE magic, and okay, somehow you get these guys on the left-hand side. Okay, so now let me maybe make this a little more precise. So we have, well, we kind of want to measure the failure of LG to be an equivalence. And we have to use a certain algebra. So algebra with this check producing. We know that. LG with the 16. And then another key assertion was that not quite this coef, but the fancy coef functor was conservative. So that allows us formally to reduce, well, kind of, okay, we're showing that this algebra is trivial. So we need to show. And it's an algebra, so it has a unit map. So it's not just that it's abstractly trivial, but that it's really trivial. There's no reason. Okay. So here is. Okay, and okay, previously I said that we know everything on the Eisenstein part in terms of this reformulation of the problem. The statement is that if I restrict to the formal completion along reducible local systems, this map is an isomorphism. So this restriction along okay, I reducible map check formally completed along the closed subset of reducible local systems. Okay, so you know that restriction. So on the reducible locus, everything is okay, and then we need to say something about the irreducible locus. So it remains to study this map. So look, you check irreducible. Going to AG and okay, it was delivered task. So well, definitions. Now let me summarize what we actually know about this AG task. Facts. The first thing I claim is that this AG cusp is a classical vector bundle. So it's really well, the family of vector spaces finite dimensional. But actually, something even better is true. It's not just any old vector bundle, it actually has a canonical connection. And not only does it have a connection, but it's like a really, really finite kind of connection. So it comes from it's a connection. But coming from the finite default local system. So let's say this finite
Regular copy.
what?
Regular copy.
Yes. Because finite finite is what's finite. Thank you. Let me explain why this is very close to results that were previously studied. So maybe 2.1. So something that is proved in this talk. Okay, it was not quite this statement, but he proved that AG cusp is a perfect complex. So then I showed. I'll explain that AG cusp is not only is a perfect complex, but it's self-dual. This was a consequence of ambidexterity. Therapy. Now I need to tell you why it's classical. And the key input for this is, okay, so I want to show that this perfect complex is cuspal. Oh, sorry, this AG cusp is a classical vector bundle, so I need to look at its fibers and show that they live in the heart. So what do we know about the fibers of the AG cusp? So explain. So this AG cusp really just measures something about overs. So that's where overs enter. At least for the first time in this talk. So if I take the fiber at an irreducible local system. This is the homology of a certain space. It's the space of generic superstructures on sigma. So generic. Sigma. And this was some, okay, it was not like a finite dimensional space, but it was kind of equivalent of proper things. So you can think that it's basically proper. Okay, so this is homology of something in particular is connected. And by the self-dual property, it's also co-connected, so it's more. That proves the first. Now let me say a little informally how the second assertion is deduced. So again, okay, so we have like some, well, just like something which has to do with the homology of something proper. And if we're looking at a proper scheme, you could apply the Stein factorization and you have connected fibers, and it's something finite, but maybe only at the generic point. And this kind of, okay, that's the mechanism. I won't say that. Okay, so any questions about this?
Well, you should say that it's because it's H0, that's why it's counted on.
Yes.
That was fine reflection, that's if I'm not finding on the drawing, but here.
Yes.
With the proper and with H0 because of the one, we need to here have to look and connect the components of the
Yes.
that will be fine.
Yeah, exactly. Okay. So this suggests a way to just finish the argument. So we wanted to show that this map is an isomorphism. Okay, you can check it on fibers, and on the right hand side, okay, there's just an explicit formula. We just need to show this space is compatible. This is not obvious. In fact, it's not even obvious that this space is non-empty, but I guess Dino proved this many years ago. But of course, not every non-empty space is compatible, so that doesn't quite finish the argument. So, so this space non-empty. And then there was later work of Durango, Partan, which just proved that this space was compatible, at least if the group is classical. So,
in your explanation of keyword, there was something you're using that's like the actual algebra structure on it. As
no algebra ever. I'm not using algebra structure at all.
okay. Okay, I'm getting it. You said again?
I'm saying yes. Well, maybe ask your question if this you will indicate that algebra structure.
Okay, so we have AG now, which is literally going to be 0.
Yes.
We just move back to normal.
Yes.
So where the hell is the connection from? Oh, sorry, where is that?
Okay, let's say I have a proper morphism. You're happy so far. Proper morphism.
Where is the people? What is the?
So this is basically this space mapping to locus irreducible is basically proper.
Yes.
So we're counting.
Now let's suppose it was actually finite.
Okay.
Like it's not actually proper, it's not finite type, but ignoring this.
Okay, fine. This is right. So a priori, so you're saying the two. There's no assertion yet of any compatibility between that connection and okay.
No.
Okay.
Yeah.
Okay. Right.
So okay. So maybe I should have applied obliv.
Fine.
So you're correct. So strictly speaking, I did not define as precisely as well. Okay. So
You have a reference on first statement with never sorry on law or the non-emptiness of space.
it's a paper of demografic progress and other powers. What? Rinkin and others. I think it will bring it up. Okay, I'm 50. What? Okay, so it's. Okay, so please.
Kevin, just checking the following, at this point, because of one, it's enough to know connectedness.
Yes, absolutely, but they actually prove, well. Cosky proves things.
In that term, they don't know this self-use, so.
Yes.
Yeah.
Yeah, the paper is called irreducible connections that meet generic Walker structure.
Okay, yeah.
It's enough to do connectedness, and it's pretty much, well, it's enough to do it for a single local system, and each component process. Basically, this measure is so. Yeah, just choose your reducible local system, the opera structures on it, show it's connected. And then you're like, oh, God, how did I actually? Like, someone gives you two opera structures, and you just have to deform one into the other. Yeah, just like that.
Yeah, so, okay, not obvious how to do it, but it would. At least some maths. Okay. So now what I want to explain is somewhat, well, okay, how you actually finish the proof without using this necessarily.
Correct, that like this BKS result would imply like the vector class of the possible.
Yes, absolutely. So, yeah, so your own, if you don't know about EH, then like you don't. I do know there are other non-classical groups. So, any other questions before I conclude? So now, I'm going to make some further assumptions just to simplify matters. So I'm going to assume that, each track is simply connected.
Oh, maybe you can comment that also the contractibility in the case of type A is really easy.
Yes. So, yes. I guess just.
So what do you know is sense? Like the cyclic vector is the generic one. It's too simple. You don't have to think hard about what an opera structure is.
The other possibilities, like this, harder.
Yes, there's a more complicated but quasi-explicit description.
That's what you got.
Yes. Okay, so G check simply connected. Three units is equals 2. Now I'll just state some more facts. So, maybe I'll do it on that form.
Yeah, I think that's.
More fact. So let me again emphasize, so G check is simply connected. Use out these 2. So the first of these more facts is so one thing we might have said is that you need derived algebraic geometry because Lopez's G check is a derived set. So fact 1, Lopez's G check is classical. So in this case, actually, it's not a derived set. Maybe here the reference is PD1. So at the point where Dima introduced the notion of quasi-smooth, he said that this is a derived notion of being LCI. And the way you can show that something is classical LCI is that first you show that it's quasi-smooth, which we know about this. And then you need to know that it has the expected dimension. And that's how this assertion is proved. I won't say more about that. Then there's, okay, so actually we're interested in this locus of irreducible local systems. And another assertion is that this has codimension 2. So it's just some random true fact that we'll use. Then another true fact we'll use is that this space is simply connected. Not hard to imagine how this is going to be used. And so for both of these, I need to know that G check does not contain. Well, the null factor of G check is SL2. So no. So in that case, you have to do things. Okay. There are many ways you can just need it. And then the last fact we'll need is something about AG. So far I haven't said anything about AG itself. And the assertion is that you take global sections of this AG plus AG itself. This is a one-dimensional vector space. Okay, so somewhat disjoint logically set of facts, but we'll collect them somehow to finish the argument. And then I'll say a little bit about how to think about these assertions. So why does this line is feature reducible is AG. Okay, let's see what we know. So we have this AG cusp. It's given by some local system, and it's a local system of something irreducible. Oh, sorry, something simply connected. So it's trivial. So fact 3 implies that AG cusp really just O to the power of whatever the rank is. It's just some trivial vector bundle. So I need to show this number, rank is equal to 1. How do I find out what this number is? I guess I have to test this object somehow, and okay, let's consider its global sections. So let's look at global sections. Looks is G check reducible. The G cusp. So this is the same as global sections of O. With some power. Now, among these facts, I didn't tell you what global sections of AG cusp is. I only told you about global sections of AG on the whole thing. Let's compare this. Certainly, there's a map. And okay, so I want to say that these, okay, this is just K. By fact 4. I want to say, let me go to the human level. So H0. I'm ascending. Okay. So I want to say that these are the same. Here's an incorrect argument. I removed something of codimension 2. This is not supposed to change global sections. Okay. How do you fix this argument? So first of all, well, the difference between AG and AG cusp measured by local cohomology along the reducible locus. And we know what AG on the reducible locus is. It's the same as O. Now that argument should work with the caveat that locus is not smooth. So if we were on something smooth, then removing codimension 2 set is unproblematic, but doesn't really have to be smooth, so it works with your classical LCIs. Let me just say that. So more precisely, the difference is just some local cohomology group which of O, and that vanishes, well, basically by 1. Okay.
I want to take this next more.
Yes. Yes. Yes.
Okay.
I'm in algebraic geometry. Codimension, like
Okay.
actual code.
You mean the content of codimension of code?
Yes.
Sorry, the comparison. This is exactly the truth. If you are like reducible.
Reducible.
There's two letters.
It's not really red,
Yeah.
yeah, it's okay.
So that the unique is the isomorphism?
Yeah. So it's an algebra.
It was a great, it was the same question.
Yes, so like one is not zero in an algebra, and the algebra is zero. Okay. So this explains why these more facts imply this isomorphism. Okay.
So you prove that. You prove that. Look, H0. Rank number of copies is.
What?
Could I input the machine one? You need that.
Sorry, say that again.
Because you need regularity code and mention what, you know, this is part of the other.
No, I don't think so.
But it's a regular code and mention.
Not to my knowledge.
So
Maybe.
it is slightly more further, so you. So. What do you, which is something did you prove?
So that map is an isomorphism,
Yes, okay.
given these assertions.
Yes. And particularly deduce that rank is one.
Yes. So you have some vector space. If you take rank many copies of it, you get K. It follows that the number of rank is one. Doesn't matter what vector space you started with. Oh, okay.
Assuming locus is non-empty.
What?
Assuming locus is the.
Did I?
If you need that, so.
Yeah.
No, that's okay. That's a composition for. Okay, legal question.
I just irreducible.
What? Okay,
Doesn't matter.
is everyone satisfied?
Why can we just, when did we reduce to G simply connected again?
I did not explain this,
Okay.
so you must do more work. It's not like really okay. You must do something, but just for simplicity, I'll pick this one.
In some sense, 50% of that paper or something, like the paper would be a lot shorter. But 50% of it is a reduction. Well, explaining how you get past the simplest.
Gotcha.
Okay.
I mean, it's something very interesting, but I just yeah.
But it's completely games with finite abilities to use.
And what about the genus assumption?
That's
So in genus 0, like everything is Eisenstein series. And in genus 1, there's like more games. So I guess if you're in type A, okay, you can use anything you want. There, yeah, many things are known. And then aside from that case, actually, again, this is actually.
I would like to say, like naively, you think these two computing matrices, like that's what a representation of the fundamental group of the elliptic curve is. We think that they all apply in Borel, something like this, right? That's definitely through theorem of linear algebra. This actually fails. There are irreducible local systems for like PDL2, for example, but outside of type A, there are no weird counterexamples like that. Fun answer to this. I don't know if you construct that thing. It's Burrell and Friedman and these formats. So you can just
I also asked, like, now is it known that like this type of generic structures is calculation?
Yes, because if you believe everything, this is okay.
Well, truck,
Like actually contractible.
yeah,
I don't know.
Wait, no,
That's
it's
what
always very hard. Oh, what connectable?
yeah, what if the like a. That's element of the.
K pi like a point model finite group. I don't know.
Okay.
Yeah.
You need to indicate us.
yeah.
I think it's all in board.
Yes. Okay. Great. Okay, let me now move on to some discussion of these facts. So now, let's think about local systems and the underlying G-bug. I'll be thinking about this. Who's set up two? So I want to look at just the forgetful map onto one G check. And something Dima explained is that the fibers of this map, okay, they could be empty, but if they're not empty, they're really affine spaces. So you can try to understand something about Lopes G check in terms of this map. And now something that has been kind of appearing sort of in this conference is that inside Bungee check, there's some, well, fairly large open subset. The locus of stable bundles. It's some open subset of codimension, at least codimensional complement. At least two, at least this is why I need that there's no SL2 fab. Let me just tell you what this subset is in the case where G check is SLN. Let me see if you don't know. So in this case, an SLN bundle is okay, the rank and vector bundle, and the determinant is supposed to be trivialized. And such a bundle is stable if and only if every sub-bundle has negative degree. Bundle B5 B has degree of E prime negative. Then there's a harder Sinhan theory which generalizes this concept to any reductor. But it's easy to believe that this is some kind of or so. Now the point is that over this locus, this map is particularly nice. So let me call this locus G check state. So I'm looking at local systems whose underlying bundle is actually a stable vector bundle. And it's known in this case that this map, it's just an affine fibration. So all of the fibers are not empty and the same affine space. It's also known that any local system whose underlying bundle is stable is actually irreducible. Maybe the most difficult assertion to believe is that this map has non-empty fibers. So you kind of know that if the fiber is not empty, you know it's a torsor for a certain cohomology group, and you kind of believe that any cohomology is provable. But how do you show that this map has non-empty fibers? So just in case you've never seen these things before, I'll tell you. Okay. Actually, I can. So thing. So like, what is the obstruction to a G bundle admitting the structure for local system? It's something called a Tia class. So the obstruction to a G bundle PG check admitting a connection is the Tia class. So this is the class I'll call it alpha. It's a class in a certain cohomology group. It lives in H1 of the adjoint problem. We'll fix it by me. The 1 0 group. You check. No. This is the same as this group. then one can just show by hand that this group vanishes if the bundle stays. So I won't say how to do this. It's very fun to do this.
Maybe just one comment about this, would be great if the board revealed. This, is that there's a very classical theorem of Bay that says the following. So first, it's easy to see that a line bundle on a curve has a connection, if and only if its degree is 0. And more generally, in higher rank, a vector bundle on a curve has a connection, if and only if every direct sum end of that bundle has degree 0. And then the fact is just these stable bundles in the SLN case, if you just look at the definition, they're indecomposable. They can't be written as direct sums of two bundles for the simple reason that both of those sum ends would have to have degree less than 0, so the degree of the guy would be less than 0. Just not. And so that's just all that's happening in this case.
Yeah, this is something really classical and some very concrete fact about bundles and curves. Okay. And okay, that's kind of the explanation for why 2 is true. And so now why is 3 true? So why is this irreducible locus simply connected? Well, let's look back at this diagram. Actually, this locus is smooth. Okay. So another classical fact is that 1G is simply connected if G is simply connected. And by this co-dimension 2 assertion, we get that the locus of stable bundles is also simply connected. Then because this is an affine perturbation, this space is simply connected, and then again, like co-dimension 2, this is simply connected. So, oh no, very bad for what okay. It's simply connected. Yes.
Revere's objecting that you didn't prove 2.
Well, I'm explaining how it is proved, not getting the proof. Okay, I'll prove that.
Can I feel
But then
I don't see why 2 is required.
So how do you know that you
Well, because you know what happens on the formal neighborhood, so when you extend from an open set, you have a filtration. And we can talk about.
okay? So does Gabir actually have like please ask your question if you have one. We do.
no, it's more involved arguments to show 2.
But the co-dimension is
If you knew the whole thing was an affine integration between using fibers, then there's no.
But anything. So maybe I'm saying something dodgy. Okay, yes. So, yeah.
In some sense, it's very similar to the argument that the complement of stable bundles inside of 1G as mentioned very example. There's sort of additional complications in the drawn setup, but not single.
Cool. Yeah. Okay. Okay, now let me just continue, okay, to the last point and say what the mechanism for this involved is. Okay, so this is something, actually Dennis already kind of explained. What? Yes. So this is something in some sense that Dennis kind of explained already in a different form. So let's look at what this global sections is. So taking global sections of this AG, by definition, AG was well, obtained by applying this Lonat. Okay. Now I can do a junction. This is really endomorphisms in V of 1V of LG left adjoint applied to O. And the left adjoint of LG, as we saw, takes O to the Poincare vacuum. This is Poincare. So we really just need to compute endomorphisms of this particular object. Dennis told us what we know about the geometry of this Poincare sheet vacuum. So what happens is that, okay, so this Poincare sheet vacuum is the quick forward of a certain D module on one end with a twist to one T. And this map factors through its quotient by T. Factors through a locally closed event.
So here we use assumption regimes.
Yes. I use in many places I use it. Yeah, in particular, this requires the assumption that these are true. Okay, so I really only need to compute endomorphisms of the push forward here. Let me call this map. Nothing. Now, what was the sheet that I was pushing for? It came from the exponential D module on A1 via a map to, I guess, some affine space, which measures some extension classes defining your n bundle, and then you add up all of these numbers and you get number one. So it came from the exponential sheet here, and there is such a diagram. And the fibers of this map are contractile. Yes, you know, put it good. But it basically is more X. So if I want to compute endomorphisms of this guy, okay, because this map is so pretty close, I can compute endomorphism of my sheet here, and by contractibility, I can just compute it. So really just so this and group is and I will but it's not up to let me again say what is really happening for SLT. That's to be representative of the general case. These it's definitely something that has been explained before, but we might as well say it again. So for G something, which is strictly speaking, not one of the cases of G check that I allow myself. Okay. What is 1 and omega? Well, 1 and omega, by definition, well, this case classifies extensions of this. So extensions of active numbers. So it's really H1 of X. Yeah. This is so my space 1 and omega is really just A1. And the torus is Bn. So I'm looking at a certain sheet on A1 modular. Okay. So so this lives on A1 modular. this is definitely something you can compute explicitly. So this is like an actual exercise that you can do. Which is that. So it's inside, highly recommend it. It's very fun to do this computation. So inside A1 mod GM, there's the open strata, which is GM mod GM. Point. So moving in this stack. And what you get is just the star extension of the function. Okay, so it's one. And the morphism of this is obviously trivial because the point is that's what happens for SL2, and then in general it's kind of just a product of this situation with itself several times. The same happens. Okay, so that's how the mass calculation is done. So okay, just that's connected function. With questions.